All right, good afternoon and welcome to CS225. I feel really, really loud. So let's fix that real fast. All right, this seems a little better. There we go. Okay, so welcome to CS225. So there's just one big announcement to kind of make sure you're up to speed. There is a exam starting this Saturday. This is exam number 4. So make sure you have registered for that so far. So you, as Cindy discussed on Monday, there will be 2 questions on this exam like usual. And one of them will very closely resemble what you're doing in MP4. And the other one will very closely resemble what you did in lab trees. So like you saw in exam 3, you have different, that the data structures you see are going to be very close to the data structure you've already seen in the trees and the exams. Yeah? Say what? Okay, yep. Sorry, I think I killed it too much. Okay, is this better? Yes, no? Okay. Awesome. So just to reiterate real fast, exam 4 coming up, make sure you're registered for a time slot. 1 question, lab trees. The other question is going to be very similar to MP4. So if you know the data structures that you use in both of those, the exam problem should look very, very familiar. So just like in exam 3, you saw a list node class that contained a list class that contained list node structures, and you manipulated linked lists. You're going to see the exact same structures, but asked to do something slightly different than what you've done before with them. So that is coming up in just a few days for all of you guys. Any questions on kind of how the course is running? Yeah. Do you have to what? Do you need to know how to use a vector class very well on the exam? No, we're going to focus on just trees and stacks and queues. So we're not going to really focus on the vector class. But you should expect a stack or a queue. Yeah? Will GD be available? We're going to start making sure that we make GDB available, yes. So starting with exam 4, you'll definitely have GDB available. All right, any other questions? Awesome. So as you notice, I am not Cinda, I'm Wade Fagan-Olmschneider. I'm the other instructor for this course. So I teach the honors section and sort of do a lot of the back-end stuff for the course. So Cinda's out at a conference called SIGSI, which is one of the top conferences for computer science education. So she's going to be coming back with a lot of like cool ideas and awesome things that other people have tried and kind of best practices. And so she's going to be out the next couple of days at that. So you'll see me here today as well as Friday, and then Cinda will be back next Monday. So we're going to just pick up where Cinda left off. So there is so up until this point, you guys have looked at problems on binary trees where you could solve them using the structure of the tree. So if we look at this code, we can see that there are 3 pieces of code here. There's the first operation, the second operation, and the third operation. And these 3 operations exploit the structure of the tree, the connectivity within nodes, by saying I'm first going to take care of my left subtree, I'm then going to take care of my right subtree, and then I'm going to take care of the current root node itself. And we can recursively apply this algorithm so that it doesn't actually matter if we're applying it to the node 38 here at the top of the tree, but we can apply the exact same algorithm where 51 is the node and we have 2 subtrees. We've got this beautiful recursion that works because of the structure of the tree. What we're going to find is we're not always going to be dealing with problems that directly relate to the structure of the tree. So you've looked at in-order, pre-order, and post-order transversals. But we want to start off today by the problem that Cinda left you with on Monday, which is how do you do a level order transversal? So what is a level order transversal? Yeah, so I saw a few of you kind of just drawing lines. So it is printing out the value of the nodes based on the level that they're on. So you start with everything at the top level, then everything at the next level. And by convention, we'll go left to right. So let's see how this actually plays out. Let's come up with an algorithm and then run this algorithm to make sure that we actually have a level order transversal. So the algorithm I'm going to propose is going to use a data structure that you've already learned. So we're going to assume that all of us in here knows how to use a queue. And we're going to exploit the fact that we understand a simple data structure to build a more complex data structure. So I'm going to say the algorithm in English, the first thing I'm going to do is enqueue the root. Then the second thing I'm going to do is while the queue is empty, or not empty, sorry, while queue is not empty, I'm going to do three things. First, I'm going to remove, I'm going to dequeue, we'll just say dequeue. An element. Print or yell it. And the third thing is enqueue its children. So this is an algorithm that only has 4 steps. We're going to start by adding the root to a queue and use this queue structure to remove the element that's on the top of the queue, process that element, and then add all the children to the queue. So let's see if this algorithm actually works. So what's the first? So if I have the root of my tree being this top element, the first thing I'm going to do is add this element to the tree, right? Or sorry, add this element to the queue. So I'm going to add plus to the queue. Now, is the queue empty? No, so what do? I dequeue, which gives me the plus element. Okay, and now what do? I'm going to yell plus. Okay, we can do this. So our program's going to yell plus. And we'll do that for all the other elements, so you guys will get used to this. And then enqueue its children. So what are the children to plus? Minus and times. Okay, and as we yelled plus, I'm going to make sure, so things we have said is plus. All right, so now we go back to the beginning of the while loop. Is the queue empty? Is the queue empty? No. When we dequeue from the queue, what's the first element? Minus, so what do we do with it? We say, we're supposed to yell minus. Minus, awesome. All right, so I heard everyone yell minus. We'll do better for the next one. And then we add minus's children. What are minus's children? So I heard some people say divide. I want to keep my code really consistent. I want to try and eliminate edge cases as much as possible. So what is the left element of minus? Null. I'm going to go ahead and put null in my tree, or in my queue, I'm sorry. And then what's the right child? Slash division. All right. Okay, so what's the next element in my tree? Star. Because I'm going to look at the top element in my queue. I'm going to yell asterisk. And then I'm going to add asterisk children, which is D and E. I find the null pointer. I do nothing. I look at the division. And let's see, right here, before I start to look at division, what has, or before I even looked at null pointer, sorry. So what happened at the point I got to where I drew the vertical bar? Yeah, I've printed out the first two levels. And what's happening to the left of the vertical bar? The elements in level order are being added to the queue. So let's write the code for this. Let's see what this would look like in our code. So at this point, we're going to just assume you have a queue. So we'll go ahead and say queue. And then we'll go ahead and say the first step is to enqueue the root. So queue.enqueue the root while not queue.isEmpty. So while the queue is not empty, then we're going to do three things. First thing is we're going to have a tree node pointer. T, which equals a queue.dequeue. Second thing, we're going to say, we're going to yell T at data. And the final thing we're going to do is enqueue the children. So queue.enqueue T at left. And queue.enqueue T right. Okay, so if we run this code, I think if we start where the bar is, something bad's going to happen. Whoa, segfault. Ooh, that's my least favorite word. It is one word in my world. So where are we segfaulting? At which line? Someone know? Someone want to definitively, or someone want to say which line? Yeah. Oh, I'm segfaulting in the yell line? Oh. Okay, why? Can someone help me out with why is yell segfaulting? I'm accessing data. I'm dereferencing a null pointer. How is that pointer ever becoming null? Yeah, because the child of some of my trees have null pointers in them. So there's two ways to fix this. So the first way is we can protect all of these accesses by making sure that if t does not equal null. So we can make sure that if t does not equal null, then we actually enqueue and dequeue the left child. So if we use this code, we can go ahead and create our queue, and we can see what's going to be on our queue. So we have a null pointer, we have division, So we're looking at division node. We're going to queue on B and C. Then we're going to look at the D node. The D node's children are null and null. Then we're going to look at E. The E's children are null and null. Then we're going to look at B. The B's children are null and null. Then we're going to look at C. The C's children's null and null. Then we look at all the nulls. And do we have a level order transversal? Yes. Does somebody not like something about this? Are we all happy with this? So you don't like that there's so many null values in the queue. Okay, how many null values get put in a queue? How many null values are there in the tree? N. Yeah, so it's n plus 1. So this is what Cindy told you guys on Monday. You've got n plus 1 null values. Should that concern us? Is that too many? So how many pieces of data do we have? N. So are we actually increasing, is there an increase in the complexity of this algorithm because of the nulls? No. We're just adding a constant factor. Basically, we can think of it, for every data piece, we have a null. So we don't need to worry about it, but it may make some of you guys cringe. So how would we fix this if we wanted to avoid having the nulls? What would I need to change in my code so that we don't put nulls in the queue? Yeah. Yeah, so I need 2 if statements, right? So I'm going to check. So I'll use red to differentiate this a little bit. So I'll say if t at left does not equal null, and if t at right does not equal null. Okay, so there's an additional amount of complexity in the code. We have to handle more edge cases if we check each individual child. But for handling more edge cases, we have a cleaner underlying tree where we don't populate it with nulls. So both of them are totally correct answers. They are both valid ways of creating a level order transversal. So how many of you guys, if you were to think about programming this yourself, let's say this was, in fact, this is something that actually should look very familiar to you. What does this look like? I heard someone say that. MP 4.2. They're adding things to queues and taking them off. So this looks exactly like BFS. So you'll see it when we go work on graphs as well, that this idea of adding elements to a queue is going to be a very common pattern we see. So this is not the only time you're going to see code that looks like this. So looking at this, how many of you guys would write the code in the green with one if statement and putting nulls in the queue versus how many people would write the code in the red? So how many of you guys would write the code in the green yourselves? Do you find that more elegant? Show of hands. How many of you guys would write the code more like the code in the red? Lots of kind of people wanting that efficient list there. So again, this is a matter of design, and both of them produce the correct output running in the same running time. Any questions? So we have, oh, was there one? No? Okay. We have a bunch of different ways of traversing trees now, or traversing trees now. But now we're going to move on and find another application of trees that makes trees extremely powerful. And I think this is the most important abstract data type you will see all semester long, at least as it pertains to how much you'll use this in your career and other programming languages. So one of the most core abstract data types is a dictionary. So a dictionary data type associates a key with data. So for example, you may have a bunch of courses, and the IDs might be the name of the course, like CS225, and we might have data about their average historical GPA. So the average historical GPA of 225 was 308. Not too bad, especially looking at 391 is a 293. Oh, and look at Calc 3. Oh. If you haven't taken Calc 3 yet, I think Calc 3 is a prereq to this, right? Something like that? Or just Calc 1. Okay, then if you guys haven't taken Calc 3 yet, get ready. So these are the different GPAs. The key here is a course, and the value is a numeric number. This might be a float value. This is a GPA. So we have this association between keys and their values. And there's a lot of these associations. You can see almost everything you think about where you have data associated with a value ends up being organized in a key value pair system. So your UIN or your net ID describes your advising record. So when we look up, or your grades, when you look up your grade, you look it up by your net ID. You have a unique identifier. Same idea, URL is a unique identifier that defines an HTML page. And keys can be of any form. So the three methods, the three member functions that you always have to have in a dictionary implementation is going to be an insert, a remove, and a delete. So after that, I see these weird letters. What is this K and D? What are these letters? So what is this? What are these things? Yeah. So but they're still just K and Ds. Yeah. Yeah, they're templated class types. So they can be anything we want them to be. So they can be any type. And does K and D have to be the same type? Not necessarily, yeah. They can be the same type. It's totally okay for K and D to be the same type, but they can be different types. We're okay having the string being the key here and the average GPA being a float, the value being a float. In fact, often you'll see that the type of data that's in these structures is probably going to be a pointer to some other type of data. So you might have a flower, you might have an animal, you might have a person, you might have an accountant statement. Any type of data can be used as both the key and the value. So a dictionary is an abstract data type. We talked about this dictionary without talking about how the dictionary is implemented. We're going to see a number of different implementations of a dictionary throughout this entire course. So there's many different ways that a dictionary can be implemented in code. And each of them have their advantage and disadvantage. So the first way we're going to look at implementing a dictionary is through the binary trees. So whenever we draw a binary tree that's being used as a dictionary, we're going to represent it in a particular way. Specifically, every node every circle is going to be a node, and its key value is going to be stated in the node. So this node has a key value of 3, but it also has data associated with it. So it has a pointer that might point to a flower. So every single node has a key, then a pointer to data. So even though the only thing you see is the key itself, every single one of these nodes have an associated piece of data. So let's say we want to find the value, the element with the key 4. So I'm going to find the element 4. I'm going to find 4. All right, so I'm going to go ahead and just sort of do an in-order traversal. So tell me when to stop. Going. Should I stop yet? Okay, awesome. Oh, that was a lot of work. So we don't want to be searching through the entire tree. So we could do any strategy used here is going to result in you, in the worst case, searching the entire tree to find where the element exists in the tree. So let's look at imposing a constraint on our tree to make this better. So this is one of my favorite data structures in the world. So we're going to take a binary tree and impose just a really simple constraint and make something amazing. So this is a binary search tree. So how does this tree look different than the tree on the previous slide? It's sorted. Is it sorted? It's sorted in an in-order transversal. So let's be a little more specific. So we could see if we do an in-order, if we visit our left node first, then print out the center node, then visit the right node, we do have an in-order transversal. So the in-order traversal of this becomes 10, 12, 13, 25, 37, 38. So we can do an in-order traversal, and it's sorted. So what does that imply about the left subtree of every node? Yeah, all of the data is smaller. So we can actually define a binary search tree as a binary tree such that, how do we always define a binary tree's definition? The tree may be empty. So you're going to see every construction of a definition is going to begin with such that tree is equal to is empty, or the tree that has the value that has the node R and a left subtree and a right subtree, where the element x is in TL if the key of x is less than the key of R. So if the key of my x is less than the key of my left subtree node is less than the key of my root, then it must be in the left subtree. And what's the condition for the right subtree? Yeah, it's going to be greater than. The key of x is greater than key of R. So there's a great question. What if they're equal? it doesn't happen? It just stops? So this is going to be something that's a little bit implementation dependent. So the big idea is that we're going to assume that every key has to be unique in our dictionaries. So if the key already exists in our dictionary, we're going to throw an error or just do nothing. So we're not going to worry ourselves about duplicate keys. And you can have a design discussion on what you should do and how you should alert the client that they're trying to insert a duplicate key. Right now, we're just going to assume that we're going to do nothing if we find a duplicate key. So we're not even going to include the equal case in here. We're going to, in fact, say that it's not a valid binary tree if you have two nodes that are equal on different levels. That every key, by this definition, is unique. OK, so let's create a binary tree. So I'm going to argue that I have a node 37, 32, 53, and we'll say like 13. OK, so this binary tree, 37, 52, or 32 is less than 37. OK, that's fine. 53 is greater than 37. OK, so it's a binary search tree. No. But my definition held. So what are we thinking? You have to check all the levels, but I can't, like, mathematically, check all levels doesn't. So is there a nice, concise way of saying check every level? Can we use the recursive nature of this tree? So we want to make sure that the left tree is just like our root itself, right? So we want the left child to be less than the current node, the right child to be greater than the current node. And for TL and TR are binary search trees. So complete definition is that the key of the left subtree is less than the key of the root. The key of the right subtree is greater than the key of the root. And each subtree are binary trees themselves, or binary search trees themselves. So now we have a complete definition for a binary search tree. Any questions? So this is a powerful data structure. So let's actually look at implementing it a little bit. So what we'll do is every time we have a binary search tree, we're going to generally have some sort of a class structure that will have a tree node element in it. So you've seen these tree nodes before. But the only difference is now our tree nodes have both a key and a value associated with them. So we have data D and key K. And these, again, are template types that need to be defined when you define the structure itself. They can be the same type. They can be different types. But the type of the key must match all of the keys you insert in. Type of the data must match all of the data you insert in. So this is a basic tree node structure where the only thing we've added is we've added a key element, and we're going to impose some constraints on how we construct the tree. So Cigna did not mention an implementation for insert and remove. Because insert and remove are sort of ill-defined in a simple binary tree. So there's not necessarily a structure that you need to maintain. But now we have a very defined structure that we have to maintain every time we insert a node and every time we remove a node. We also need to find the nodes, and we probably want to be able to traverse the list so that we can kind of print it out, give an in-order printout of a binary search tree. So let's look at the easiest of the functions. So I want to find the element 42 in this tree. So how do I find 42 in this tree? Where do I start? Yeah, I start at the root, and then I'm going to compare. I'm going to compare 38 with 42. 42 is greater than 38. What do? I go right. So that's one comparison, right? 51, 42. 42 is less than 51, so I go left. It's a second comparison. What happens if I go, so now I'm at 40, left or right? Right. So did I find 42 in this tree? So I can definitively say I didn't find 42. All right, so here's a fun quizzes question. Give me a number that requires 4 comparisons to find. $66. So let's see if 66 takes 4 comparisons. So I'm at 38. So is the final comparison, I'm going to say how many value comparisons, let's put it that way. So you may, depending on how you implement it, you may or may not be evaluating that null. That's going to be implement dependent. But that's going to be a pointer comparison, not a value comparison. So it may be, how many value comparisons do you need to make 66? So looking for 66, we're at 38. Where do we go? Go to the right. Where do we go? Left. Then I found it. Awesome. So how many comparisons did I make? 4. So you should be able to be really comfortable with looking at a tree and traversing it to both find a node, and then in a minute, we'll also use this to insert a node. So let's go ahead and write the code for this. So what is going to be so we're going to return a tree node star, and this might be part of a binary search tree class. This is a find function. So return type is a BST star. It's in the class binary search tree, or BST, and we're defining the function find. Is this going to be a private or a public method? Private. Why is it going to be private? Why do we think it's private? Yeah, so you're returning a tree node. You're returning the structure of the dictionary, not the data itself. So you can have a wrapper that returns the data of this. But the client code should not care how you implement your dictionary. The client, if you look at the abstract data type needs to get back data and keys, not tree nodes. So there may be a wrapper class, there may be a wrapper function that calls this function, but you should never return a tree node to the client code. Okay, so we've got this function. If c-root is equal to null, what should we do? What does that imply? If we reached a pointer that's null, we didn't find it, so we know that that value is not in the dictionary, so we can just go ahead and return null. Awesome. Else if. What happens when our key is the same as our key? What did we do? What's the English meaning of what happened? Yeah, we found the element we wanted to find. So what should we return? Our current root. Okay, so what else should we check? What's another condition? So we want to compare we want to know if the key is less than the current root's key. This is saying if the key, like 66, we're comparing 66 and 38. If 66 is less than 38, where should we go? If our key is less than the current key of our root, we want to look at the left subtree. Yeah, so if our value that we're searching for is smaller than the value we're currently at, we want to, and what do we want to do with the left subtree? Yeah, we want to find the element in the left subtree. So we just want to return find of c-root at left. And otherwise, return find c-root right. So let's see how this works in action. So we've got this tree, and let's say we want to find the element 11, or we'll do 12. We'll find the element 12. So our key is equal to 12. So when we call this function with our current root being the top of the tree, so our current root is 38, is 38 null? No, is 38 equal to 12? Is 12 less than 38? Yes, so then we call find on this subtree. So now our current root is 13. So we're doing the exact same thing. We're making a recursive call on the left subtree where the current root is now 13. The key is still 12. Is 13 equal to 12? Is 12 the key less than 13? Yes. So now we advance to the same thing in this subtree. So we're calling find of this subtree. Our current root is now 10. So which of the four else statements do we, or which of the four conditionals do we fall into? No, 12 is not equal to 10. So we're not going to be, the current root is 10. So we're going to fall into, do we fall in the first case? Second one? Third one? Fourth one? Yeah, so the key, 12 is greater than 10, so we move to the right subtree. Our current root is now 12. which matches this. So we found the value 12. Through this recursive call. All right, what's the running time? So I've heard a few different things. So I've heard log of n. So I'm going to propose a new tree. I'm going to implement a tree, and I'm going to insert 1. I'm going to insert 2. I'm going to insert 3. I'm going to insert 4. All right, so what have I just created? This looks like a linked list. Is it a binary search tree too? Yeah. Then I just sort of inserted a sorted list of numbers into a binary tree. I made a binary search tree here. I mean, all these have null pointers here. So how many comparisons do I have to make in the worst case in this structure? N. So the running time can't be any better than O of n. Oh, there's an interesting suggestion. So we're actually going to say that the running time of this algorithm, we're going to describe not in terms of O of n yet. We're going to say that the running time is O of h. All right, so where h is the height of the tree. So what this means is if we're able to fix a height, we can say things in terms of order n. So in a tree that the left subtree looks like the right subtree, it's going to be close to log n. But in a tree where it's vastly different, it's not. So in the last 3 minutes, we're going to look at an insert function and motivate it, at least motivate this insert function. So if I wanted to insert a number 42, what am I going to do? Could I do almost the exact same thing as find? So to insert, I can simply go 42. Okay, right subtree, left subtree, right subtree. And where I found this null pointer is now the correct location for me to insert 42. So this means I can use the same logic where if the key is less than C root of key, then I need to insert in C root left. Otherwise, I'm going to insert into C root right. So the recursive case for the function is exactly the same. So the only difference is what happens. So this is going to be a void bst insert. What happens when we reach a null node? I need to set the root equal to a new tree node. We'll assume that there's that everything's set up correctly, that this constructor works. So, very last question before I let you guys go. Does this work? No, what happens? We don't actually reference it. How do we fix this? Yeah, so instead of passing by value, a pointer by value, if we simply pass C root by reference, what happens is that we have that when we pass this pointer 40 by reference, we're passing the memory of this pointer right here. So this pointer right now points to null. When we pass this pointer by reference, when we update this pointer, it's no longer pointing to null, but pointing to the new tree node. So by passing it by reference, we are ensuring the connectivity of the graph, of the tree. So what's the running time of this? O of H. Awesome. We will chat more about this stuff on Friday. See you then.